Good day everyone! This video is a compilation of all the lessons in general mathematics for the first quarter covering week 1 up to week 8.
Good day everyone! In this video, we will discuss the concept of relation and function. Let us define first the relation. Relation is a set of ordered pairs. Recall that an ordered pair is a pair of numbers wherein the first number is called the x-coordinate and the second number is called the y-coordinate. In this example of relation, we have 5 ordered pairs. 1, 2, 3, 4, and 5. Notice that the x-coordinates are 1, 2, 3, 4, and 5. This set of x-coordinates is called the domain. On the other hand, the y-coordinates are 11, 12, 13, 14, and 15. The set of y-coordinates is called the range. Aside from writing the relation as set of ordered pairs, it can also be written in mapping form. Mapping is a way of pairing x values to y values. Mapping also shows different correspondences. For example, when we say one-to-one correspondence, it means that each value of x is paired to only one value of y. In this illustration, say we pair 1 to 4, 2 to 5, and 3 to 6. It will form now 3 ordered pairs such as 1, 4, 2, 5, and 3, 6. On the other hand, when we say one-to-many correspondence, it means that one value of x can be paired to multiple values of y. Example, 1 can be paired with 4 and 5. 2 can be paired to 6 and 7. Therefore, it will make 4 ordered pairs such as 1, 4, 1, 5, 2, 6, and 2, 7. Moreover, many-to-one means that multiple values of x can be paired to only one value of y. Example, 1 and 2 being paired to 5, and 3 and 4 being paired to 6. In this case, we also have formed 4 ordered pairs, such as 1, 5, 2, 5, 3, 6, and 4, 6. Finally, many-to-many means pairing multiple values of x to multiple values of y. Example, pairing 1 and 2 to 5 and 6. And pairing 3 and 4 to 7 and 8. Therefore, we can form here 8 ordered pairs, such as 1, 5, 1, 6, 2, 5, 2, 6, 3, 7, 3, 8, 4, 7, and 4, 8. This time, let us define a function. Function is a relation where each value in the domain corresponds to only one value in the range. From the definition, since function is a relation, we can say that function is also a set of ordered pairs. However, function is a special kind of relation in the sense that every value of x is paired to only one value of y. Therefore, not all relation can be a function. Let us go back to the correspondences earlier. In one-to-one, we can clearly see that each value of x is being paired to only one value of y. Hence, this is a function. As for one-to-many correspondence, notice that each value of x is paired to multiple values of y. 1 is being paired with 4 and 5. And 2 is also being paired with 6 and 7. Therefore, since x is being paired to more than one value of y, this correspondence is not a function. On the other hand, in many-to-one correspondence, see that each value of x is being paired to only one value of y. Like 1 is being paired to 5. It is not being paired with any other value. 2 is also paired to 5 only. The same goes for 3 being paired to 6 only and 4 being paired to 6 as well. Therefore, this correspondence is a function. Don't be confused on this one, thinking that this is not a function since the value of y is being paired to multiple values of x. Remember the definition of function. It states that the case is only for x and not for y, meaning y can be paired to multiple values of x. Finally, in many-to-many correspondence, it is quite obvious that this is not a function because looking at the value of 1, 1 is being paired with 5 and also being paired with 6. Therefore, this correspondence is not a function. Therefore, among the correspondences, the functions are one-to-one and many-to-one. The other two are merely relations. If you were given set of ordered pairs to determine if it is a function or not, remember that the values of x should be distinct. Looking at this first example, notice the values of x are different. We have 1, -2, -4, 2, and 0. Thus, each value of x is being paired to only one value of y. Therefore, this set of ordered pairs is a function. On the second one, notice that 0 is being paired to 1. At the same time, the same value of x0 is being paired to 3 as well. Therefore, this set of ordered pairs is not a function. On the third example, we see that the values of x are distinct. We have 1, 3, 4, 5, and 6. Although they are paired to only one value of y. But remember the definition of functions, the restriction is only for x value. Therefore, this set of ordered pairs is a function. Moreover, if you were given a graph To determine if it is a function, the vertical line test is being used. Any function should intersect every vertical line at exactly one point. In this graph, notice that all vertical lines being drawn on the graph intersects the graph at exactly one point. Therefore, this graph is a function. The same goes for this graph. If you will draw vertical lines, notice that each vertical line intersects the graph at exactly one point. Therefore, this graph also represents a function. However, for this last graph, notice that vertical lines intersect the graph at 2 points. Therefore, since the vertical lines intersect the graph at 2 points or more than 1 point, this graph represents a mere relation. As we ended the discussion, remember that all functions are relation, but not all relations are functions. I hope that you understood the lesson, and for the next video, we will discuss evaluating functions. Thank you and see you on the next discussion. Good day, everyone. In this video, we will discuss evaluating functions. Evaluating functions means replacing the variable in the function with the value in the domain and computing for the result. In other words, given a function and a value of x, to evaluate the function, we will just substitute the given value of x to the function and solve for the value of f of x or y. Let us take a look at this example. Solve for f of x equals 2x plus 7 when x is equal to -5. To evaluate this function, we just need to substitute -5 to the given function. This will give you f of -5 equals 2 times -5 plus 7. To simplify, we need to follow the Jambas rule. Jambas stands for groupings, exponent, multiplication, division, addition, and subtraction. Therefore, for this one, we need to multiply and then add. So, 2 times -5 equals -10. Then copy plus 7. When we simplify this, -10 plus 7 will give us -3. Therefore, f of -5 equals -3. Let us have another example. Solve f of x equals 3x squared minus 5x plus 8 when x equals 2. To evaluate this function, we substitute 2 to the x of the given function and then simplify. That will give us f of 2 equals 3 times 2 squared minus 5 times 2 plus 8. In this equation, we need to evaluate first the exponent. Hence, we will have 3 times 4 minus 5 times 2 plus 8. Then, multiply 3 and 4 and negative 5 and 2. So that will give us 12 minus 10 plus 8. From here, we need to simplify 12 minus 10 plus 8. 12 minus 10 plus 8 will give us 10. Therefore, f of 2 is equal to 10. For the third example, given f of x is equal to square root of 5x minus 1, find f of 2. Since we need to solve for f of 2, it means that we need to substitute 2 to the x of the given function. And that will give us f of 2 is equal to the square root of 5 times 2 minus 1. Multiply first 5 and 2, which will become 10. So we will have square root of 10 minus 1. Simplifying 10 minus 1 will give us 9. So it will become square root of 9. Remember that square root of 9 is equal to 3. Therefore, f of 2 equals 3. For this last example, f of x equals 3x plus 5 all over 2x minus 3. Find f of negative 3. Substitute negative 3 to the function. That is, f of negative 3 equals 3 times negative 3 plus 5 all over 2 times negative 3 minus 3. Simplify the numerator and the denominator. For the numerator, we have 3 times negative 3 will give us negative 9, then plus 5. For the denominator, we have 2 times negative 3 is negative 6, then minus 3. Simplifying numerator and denominator will give us negative 4 over negative 9. Dividing two negative numbers will result to a positive number. Therefore, the final answer is f of negative 3 equals 4 over 9. As we end this discussion, remember that evaluating function always follow the Jambas rule. Jambas stands for groupings, exponent, multiplication, division, addition, and subtraction. I hope that you have understood the lesson. And for the next video, we will discuss operations on functions. Thank you and see you on the next discussion. Good day, everyone. In this video, we will discuss adding and subtracting functions. Operations of functions. Let f and g be functions. Their sum, denoted by f plus g, is the function defined by f plus g of x is equal to f of x plus g of x, meaning the sum of the functions is denoted by f plus g of x, which can be solved by adding the involved functions f of x and g of x. Let us have some examples. Given the functions f of x is equal to 2x plus 4 and g of x equals to 4x plus 6, find f plus g of x. Based on the formula, to solve for f plus g of x, what we need to do is to add the two given functions, f of x plus g of x. Thus, we will have 2x plus 4 plus 4x plus 6. What we did here is we substituted the given f of x and the given g of x to our formula. In simplifying this expression, note that we can only combine similar terms. Similar terms are terms with the same variables and exponents respectively. As for this equation, the similar terms are 2x and 4x and 4 and 6. Combining them, we will have 2x plus 4x equals 6x and 4 plus 6 is equal to positive 10. Therefore, f plus g of x is equal to 6x plus 10. Let us have another example. Given the functions f of x equals 2x plus 4 and g of x equals x squared minus 5x minus 1, find f plus g of x. Again, to find the sum of the functions f plus g of x, we will be adding the two given functions, f of x plus g of x. Substitute the given f of x and the given g of x to this formula. So we will have 2x plus 4 plus x squared minus 5x minus 1. So we will have copy x squared, and in here we can combine 2x and negative 5x because they are similar terms. So that will become negative 3x. Also, we can combine positive 4 and negative 1, which will become positive 3. So finally, the sum of f of x and g of x is equal to x squared minus 3x plus 3. For subtracting functions, let f and g be functions. Their difference, denoted by f minus g, is the function defined by f minus g of x equals f of x minus g of x. Meaning, the difference of the functions is denoted by f minus g of x, which can be solved by subtracting the involved functions f of x and g of x. Let us take a look at this example. Given the functions f of x equals x squared plus 3x minus 1 and g of x equals 3x minus 7, find f minus g of x. Using the formula earlier in finding the difference of the two functions, f minus g of x equals f of x minus g of x. Substitute the given f of x and g of x on our formula. So we will have x squared plus 3x minus 1 minus 3x minus 7. In subtracting functions, before you combine similar terms, multiply negative 1 to the second function. Remember that when we are multiplying integers, the product of two different signs is negative and the product of the same signs is positive. So here, we will have x squared plus 3x minus 1, then negative times positive is negative. So that will give us negative 3x. And negative times negative is positive. So this will become positive 7. From here, it is very clear that we can combine positive 3x and negative 3x, negative 1 and positive 7. Since x squared doesn't have any terms which is similar to it, we simply copy it. So negative 3x minus 3x equals 0. Since it is 0, no need for you to write it. Negative 1 plus 7 is equal to positive 6. Therefore, f minus g of x equals x squared plus 6. For the last example, given the functions f of x equals x squared plus 3x minus 1 and g of x equals x squared minus 3x minus 7, find f minus g of x. So again, substitute the given functions to our formula. F minus g of x equals x squared plus 3x minus 1 minus x squared minus 3x minus 7. Again, distribute or multiply negative 1 to the second function and copy the first function. Negative times positive is negative x squared. Negative times negative is positive 3x. And negative times negative is positive 7. Here, we can combine x squared and negative x squared. Positive 3x to positive 3x and negative 1 to positive 7. So therefore, we will have x squared minus x squared is 0. 3x, positive 3x plus another positive 3x is 6x. Negative 1 plus 7 is positive 6. Therefore, f minus g of x is equal to 6x plus 6. As we end this discussion, remember that let f and g be functions. Their sum, denoted by f plus g of x, is the sum of the two functions f of x and g of x. Their difference, denoted by f minus g of x, is the difference between the two functions f of x minus g of x. I hope that you have understood the lesson, and for the next video, we will continue this lesson for multiplying and dividing functions. Thank you and see you on the next discussion. Good day, everyone. In this video, we will discuss multiplying and dividing functions. Operations of functions. Let f and g be functions. Their product, denoted by f times g, is the function defined by f times g of x is equal to f of x times g of x. Meaning, the product of the functions is denoted by f times g of x can be solved by multiplying the involved functions f of x and g of x. Let us have an example. Given the functions f of x equals 2x plus 4 and g of x equals 4x plus 6, find f times g of x. To solve for f times g of x, we have to multiply the two given functions f of x times g of x. What we need to do first is to substitute the given f of x and g of x to our formula. We will have 2x plus 4 times 4x plus 6. In multiplying two binomials, you can use the FOIL method. Using the FOIL method, we will multiply the first terms, the outer terms, the inner terms, and the last terms. Hence, in this equation, we will be multiplying 2x times 4x, which will be 8x squared. Outer terms such as 2x times positive 6, which will give us positive 12x. Inner terms, 4 times 4x. Positive 4 times positive 4x is positive 16x. And the last terms, positive 4 times positive 6, which is positive 24. From here, we can combine the similar terms. The similar terms are positive 12x and positive 16x. Then we will just simply copy 8x squared and 24. Therefore, we will have 8x squared. Then positive 12x plus positive 16x is positive 28x. And then copy plus 24. Therefore, f times g of x is equal to 8x squared plus 28x plus 24. Let us have another example. Given the functions f of x is equal to 2x squared plus 3x minus 1 and g of x equals x squared minus 3x minus 7, find f times g of x. To do that, we will substitute the given f of x and g of x to our formula, f of x times g of x. So we will have 2x squared plus 3x minus 1 times x squared minus 3x minus 7. In multiplying two trinomials, we can do the horizontal method, wherein we multiply each term of the first function to the terms of the second function. So 2x squared times x squared is 2x raised to 4. 2x squared times negative 3x is negative 6x cubed. 2x squared times negative 7 is negative 14x squared. Do the same thing for positive 3x. Multiply it to the terms of the second function. So positive 3x times x squared is positive 3x cubed. Positive 3x times negative 3x is negative 9x squared. And positive 3x times negative 7 is negative 21x. Finally, multiply negative 1 to the terms of the second function. Negative 1 times x squared is negative x squared. Negative 1 times negative 3x is positive 3x. And negative 1 times negative 7 is positive 7. From here, we can now combine similar terms. Since there is no other term that has x raised to 4 as its variable, then we can simply bring it down. Copy 2x raised to 4. Negative 6x cubed can be combined with positive 3x cubed. So negative 6x cubed plus 3x cubed is equal to negative 3x cubed. Negative 14x squared can be combined with negative 9x squared and negative x squared. So negative 14x squared minus 9x squared is equal to negative 23x squared minus another x squared is negative 24x squared. Then we can combine negative 21x with positive 3x. So negative 21 plus 3 is equal to negative 18x. And then finally, since there is no other constant term, we can simply copy plus 7. So therefore, f times g of x is equal to 2x raised to 4 minus 3x cubed minus 24x squared minus 18x plus 7. Let us now go to dividing functions. Let f and g be functions. Their quotient, denoted by f over g, is the function defined by f over g of x equals f of x over g of x. Meaning, the quotient of the functions is denoted by f over g of x can be solved by dividing the involved functions f of x over g of x. For example, given the functions f of x equals 2x plus 4 and g of x equals 4x plus 6, find f over g of x. So once again, by formula, f over g of x is equal to f of x over g of x. So substitute the given f of x and g of x to our formula. Therefore, we will have 2x plus 4 over 4x plus 6. Observing the functions 2x plus 4 and 4x plus 6, we can express the numerator and the denominator in factored form, such as the numerator will become 2 quantity x plus 2 and the denominator to be 2 quantity 2x plus 3. From here, we can cancel the common factor, which is 2. Therefore, f over g of x is equal to, so once again, we can cancel it out because 2 divided by 2 is equal to 1. So finally, the answer will become x plus 2 over 2x plus 3. Let us have another example. Given the functions f of x equals x squared plus 5x plus 6 and g of x equals x squared minus 9, find f over g of x. In dividing functions, it is better to always express the numerator and denominator in factored form. So, to do that, let us substitute first the given functions to our formula. So, the given f of x is x squared plus 5x plus 6 and the given g of x is x squared minus 9. So, the factors of the numerator and the denominator are as follows. So, the factors of x squared plus 5x plus 6 is x plus 3 times x plus 2. While the factors of the denominator are x plus 3 times x minus 3. From here, we can easily see the common factor, which is x plus 3, so we can cancel it because x plus 3 divided by x plus 3 is equal to 1. Finally, f over g of x is equal to x plus 2 over x minus 3. As we end this discussion, remember that let f and g be functions. The product of the two functions is denoted by f times g of x can be solved by multiplying the two given functions f of x times g of x. On the other hand, the quotient of the two functions is denoted by f over g of x can be solved by dividing the two given functions f of x and g of x. I hope that you have understood the lesson, and for the next video, we will discuss composition of functions. Thank you and see you on the next discussion. Good day, everyone. In this video, we will discuss composition of functions. Composition of functions. Let f and g be functions. The composition denoted by f composition of g is defined by f composition of g of x is equal to f of g of x. Meaning, composition of function is substituting a function to the variable of another function. The second function is the function to be substituted to the first function. Let us take a look at this example. Given the functions f of x equals x minus 1 and g of x equals 2x plus 1, find f composition of g of x. Remember that f composition of g of x is equal to f of g of x. Notice here that we need to substitute to the x of f of x is the function g of x. So this x will become g of x. So what will happen is substitute 2x plus 1 to the x of f of x. So you will have 2x plus 1, then minus 1. Then simplify this equation. So you will have 2x plus 1 minus 1 will give you simply 2x. So therefore, f composition of g of x is equal to 2x. Let us have another example. Let f of x be equal to 2x minus 1 and g of x be equal to 2x plus 1. What we need to find this time is g composition of f of x. So from here, g composition of f of x is equal to g of f of x. This time, what we need to change is the x on the g of x, and we need to substitute f of x to this x. So this x will become the entire f of x. So what will happen is 2, copy 2, times x will be changed into x minus 1. So that would be 2 times x minus 1 and then plus 1. From here, you will notice that the x of the outer function g became the first function f of x, x minus 1. Then, simplify. 2 times x is 2x, then 2 times negative 1 is negative 2, then bring down plus 1. Simplifying this, we will have 2x minus 1. So therefore, g of f of x is equal to 2x minus 1. Now, let us consider this example. Given the functions f of x equals 2x squared plus 3x plus 1 and g of x equals 2x plus 1, find f of g of x. So remember that f of g of x is equal to f of g of x, meaning these x in f of x will be changed into g of x, which is 2x plus 1. So we will have 2 quantity. Remember that we need to change this x into 2x plus 1. So 2x plus 1 quantity squared, because we have it squared here, and then plus 3 quantity again, change this x into 2x plus 1. There you go, and then plus 1. In simplifying this expression, we need to simplify first this. 2x plus 1 quantity squared is equal to 2 quantity 4x squared plus 4x plus 1. Then plus 3 quantity 2x plus 1 and then plus 1. The next thing to do is to distribute 2 to this trinomial and 3 to this binomial. So we will have 2 times 4x squared is 8x squared plus positive 2 times positive 4x is positive 8x. Then positive 2 times positive 1 is positive 2. The same thing goes for positive 3. Distribute it rather to the binomial 2x plus 1. So we will have positive 6x. Positive 3 times positive 1 is positive 3 and then plus 1. Okay, so combine like terms, we can combine 8x and 6x, but since we don't have other terms with the variable x squared, so we simply copy it, 8x squared. So once again, combine positive 8x to positive 6x, so you will have positive 14x, then combine positive 2 plus 3 plus 1, so that will be plus 6. So therefore, the final answer is 8x squared plus 14x plus 6. Okay, let me box it. There you go. For the last example, given the functions f of x equals 2x squared plus 3x plus 1 and g of x equals 2x plus 1, find g composition of f of x. So here, g composition of f of x is equal to g of f of x. So from here, notice that we need to change the x on the g of x by the f of x, which is 2x squared plus 3x plus 1. So this x will be changed into this function. So we will have 2 quantity or 2 times 2x squared plus 3x plus 1 and then copy plus 1 there. Okay. So distribute 2 to the trinomial inside, then you will have 4x squared plus 6x plus 2 and then plus 1. Okay, so from here, what we can combine is positive 2 and positive 1. So we simply bring down or copy 4x squared plus 6x and then plus 3. So therefore, the final answer of g composition of f of x is 4x squared plus 6x plus 3. So as we end this discussion, remember that the definition of composition of function is let f and g be functions. The composition denoted by f composition of g is defined by f composition of g of x is equal to f of g of x. And also remember that f composition of g of x is not always equal to g composition of f of x. F of g of x is different from g of f of x. I hope that you have understood the lesson for today, and for the next video, we will discuss the introduction to rational equations, functions, and inequalities. Thank you and see you on our next discussion.
Good day everyone! In this video, we will discuss the introduction of rational equation, function, and inequality. Let us define first each. Rational expression. Rational expression is an expression that can be written as a ratio of two polynomials. Therefore, for an expression to be a rational expression, both the numerator and denominator should be polynomials. Recall that a polynomial is an algebraic expression with no negative exponent nor fractional exponent on any variable. Hence, If any of the numerator or denominator has negative or fractional exponent, the expression will not be a rational expression. On the other hand, rational equation is an equation that involves rational expressions. Therefore, your key hint here is an equal sign equating two rational expressions. Moreover, rational inequality is an inequality that involves rational expressions. If the rational equation has equal sign, rational inequality involves inequality symbols such as less than, greater than, less than or equal to, and greater than or equal to. Finally, rational function is a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x cannot be equal to 0. For you to have a rational function, f of x or y would be your key. However, remember that regardless if it is a rational expression, equation, inequality, or function, there is always a restriction in the denominator that it should not be equal to 0. Otherwise, the entire expression will be undefined. Let us have some examples to practice determining whether each given is a rational expression, equation, function, inequality, or none of these. For the first one, 5 over x minus 3. See that both numerator and the denominator are polynomials, but there is no equal sign, nor inequality sign, nor f of x. Therefore, this is simply a rational expression. How about the second one? Y equals x cubed over 4x minus 2. Notice that there is a rational expression and it is equated to y. Therefore, this is a rational function. For the third one, x raised to negative 2 plus 1 over 7x raised to 1/3 minus 2. See that there is a negative and fractional exponent at the variable. Remember that if there is such, the expression will not be a polynomial. Therefore, this expression is not a rational expression, so we will be writing none of these. For the fourth one, 5 over x minus 3 is less than or equal to 2x squared over x squared minus 1. Notice that there is an inequality symbol less than or equal to. Hence, this is a rational inequality. Looking at the fifth one, 2 over x minus 3x over 5 equals 5 plus x over 3 minus x. Since there is an equal sign here, this is a rational equation. And finally, for the sixth one, we have f of x is equal to x squared minus 2x plus 1 over 7x plus 3. Since there is an f of x here, and this is a rational expression, therefore, this entire expression is a rational function. I hope that you understood the lesson, and for the next video, we will discuss about solving rational equations. Thank you and see you on the next discussion. Good day everyone! In this video, we will discuss solving rational equations. In the previous video, we have defined rational equation as an equation that involves rational expressions. These are the steps in solving rational equations. Number 1. Eliminate denominators by multiplying each term of the equation by the least common denominator. Number 2. Note that eliminating denominators may introduce extraneous solutions. Check the solutions of the transformed equations with the original equation. Let us have an example. Solve the rational equation x plus 1 over x plus 2 equals x minus 3 over x minus 5. Notice that in this given, there is only one rational expression on both sides of the equation. If this is the case, we can easily eliminate the denominator by cross multiplication. Therefore, we will have x plus 1 times x minus 5. Copy the equal sign, then x plus 2 times x minus 3. From here, we simply need to multiply the two binomials x plus 1 times x minus 5 and x plus 2 times x minus 3. So, we will have x times x is x squared, x times negative 5 is negative 5x, positive 1 times x is positive x, and positive 1 times negative 5 is negative 5. Again, copy the equal sign. Do the same thing here. So you're gonna have x times x is x squared, x times negative 3 is negative 3x, positive 2 times x is positive 2x, and positive 2 times negative 3 is equal to negative 6. Note here that we can combine similar terms. So therefore, we will have x squared minus 4x minus 5 equals x squared minus x minus 6. The next thing that we need to do is to isolate all the terms to the left side of the equation and equate this by 0. So therefore, we will have x squared minus 4x minus 5 minus x squared plus x plus 6 equals 0. Next, combine similar terms. So, x squared minus x squared is equal to 0. Negative 4x plus x equals negative 3x. Negative 5 plus 6 equals positive 1, then equals 0. To solve for the value of x, let us eliminate the constant number positive 1 to the right side of the equation. Thus, we will have negative 3x equals negative 1. Then, divide both sides by negative 3. So, negative 3 divided by negative 3 equals 1. Hence, x equals negative 1 over negative 3, which will become positive 1/3. Let us have another example. Solve the rational equation 3 over x plus 2 minus 1 over x equals 1 over 5x. In this given, notice that there are two rational expressions on the left side of the equation. Hence, we cannot use cross multiplication. To solve this, we need to multiply the whole equation by the least common denominator. To find the least common denominator, look at the factors of our denominators. The factors are x plus 2, x, and 5, and x. Notice that we have 2x here as our factor. So for the LCD, we will only be taking 1x. For that case, our LCD for this is x plus 2 times 5 times x. After determining the LCD, we can now multiply our equation by the LCD to eliminate the denominators. Therefore, we will have 3 over x plus 2 minus 1 over x equals 1 over 5x times our LCD, which is x plus 2 times 5 times x. In multiplying the LCD to the equation, we will be multiplying it by each rational expression. For example, 3 over x plus 2 times x plus 2 times 5 times x. Notice that the denominator is x plus 2 and it is one of our LCD here. Therefore, we will be canceling x plus 2, leaving us with 3 times 5 times x. Copy the minus sign. Next, multiply again the LCD to the second rational expression, but since your denominator here is x, so therefore x here will be cancelled. So therefore, we will have 1 times x plus 2 times 5. Then copy the equal sign. Finally, do the same thing to the third rational expression. Note that the denominator here is 5x. Therefore, 5 and x here will be cancelled, leaving us with 1 times x plus 2. Next, we need to simplify this term. So 3 times 5 times x will give us 15x. Copy the minus sign. Then we will have 1 times 5 is equal to 5. Then times x plus 2 equals 1 times x is x and 1 times 2 is positive 2. Next, distribute negative 5 to our binomial x plus 2. Therefore, we will have 15x minus 5x minus 10 equals x plus 2. Next, isolate all terms to the left side of the equation. Thus, we will have 15x minus 5x minus 10 minus x minus 2 equals 0. Let us combine similar terms. 15x minus 5x equals 10x minus x equals 9x. Negative 10 minus 2 equals negative 12. Then equals 0. Once again, to solve for the value of x, isolate the constant number to the right side of the equation, giving us 9x equals 12. Divide both sides by 9. Hence, we will have x equals 12 over 9. But we need to lowest term 12 over 9. 12 and 9 are both divisible by 3. Finally, we will have the answer as 4 over 3. For our last example, solve the rational equation x over x plus 2 plus 2 over x squared plus 5x plus 6 equals 5 over x plus 3. To determine the LCD, let us factor the denominator of the second rational expression. So we will have x plus 2 times x plus 3. Therefore, the factors of our denominators are x plus 2, x plus 2 times x plus 3, and x plus 3. Notice that x plus 2 and x plus 3 are both duplicated. Once again, if that is the case, we will just be considering one factor. So therefore, the LCD is x plus 2 times x plus 3. Next thing to do, we will multiply the whole equation by our LCD x plus 2 times x plus 3. So therefore, we will have x over x plus 2 plus 2 over x plus 2 times x plus 3 equals 5 over x plus 3 times our LCD x plus 2 times x plus 3. Next, multiply the LCD by each rational expression here. So for the first one, since the denominator is x plus 2, then x plus 2 here will be cancelled, leaving us with x plus 3 times x. Copy the plus. For the second one, we have the denominator x plus 2 times x plus 3. And this is also our LCD. So everything will be cancelled, leaving us with only 2. Then copy the equal sign. For the last one, our denominator is x plus 3. So x plus 3 at the LCD will also be cancelled, leaving us with 5 times x plus 2. Next, let us simplify this by multiplying x to the binomial. So we will have x squared plus 3x, then copy plus 2, equals, do the same thing for 5. So you will have 5x plus 10. Next step, isolate all the terms to the left side of the equation, giving us with x squared plus 3x plus 2 minus 5x minus 10 equals 0. When we simplify this by combining the similar terms, it will give us x squared minus 2x minus 8 equals 0. Notice that this is a quadratic equation. For that case, to solve for the x of the quadratic equation, we need to factor this. The factors of this quadratic equation are x minus 4 times x plus 2. Next, we need to equate both factors by 0. So therefore, x minus 4 equals 0 and x plus 2 equals 0. To solve for the value of x, isolate the constant to the right side, giving us with x equals 4 and x equals negative 2. Since you have arrived with two solutions, you need to check each solution if they will satisfy the equation. However, looking at the solution x equals negative 2, when we substitute negative 2 here, negative 2 plus 2 will give us a denominator of 0. Remember that denominator cannot be equal to 0 because it will become undefined. For that case, it means that negative 2 is an extraneous root, and therefore, the final answer is x equals 4. I hope that you understood the lesson And for the next video, we will discuss about solving rational inequalities. Thank you and see you on the next discussion. Good day everyone! In this video, we will discuss about solving rational inequalities. We have defined rational inequality as an inequality that involves rational expressions. These are the steps in solving rational inequalities. First, we write the inequality as a single function on one side of the inequality symbol and 0 on the other side. Second, determine over what intervals the fraction takes on positive and negative values. Third, locate the x values for which the rational expression is 0 or undefined. Factoring the numerator and denominator is a useful strategy. Fourth, mark the numbers found in step 3 on a number line. Use a shaded circle to indicate that the value included in the solution set and the hollow circle to indicate that the value is excluded. These numbers partition the number line into intervals. Fifth, select a test point within the interior of each interval in step 4. The sign of the expression at this test point is also the sign of the rational expression at each exterior point in the aforementioned interval. And finally, summarize the intervals containing the solutions. To better understand these steps, let us have some examples. Solve the rational inequality x plus 1 over x minus 5 is less than or equal to 0. The first thing to do is to determine the zeros of the numerator and the denominator. To find the zeros, simply equate the numerator and the denominator to 0 and find the value of x. For the 0 of the numerator, we will equate x plus 1 to 0 and solve for the value of x. Therefore, we will have here x equals negative 1. For the denominator, we will be doing the same thing. We will have x minus 5 equals 0 and solve for the value of x. Here, the value of x is 5. After determining the zeros, use these values to determine the intervals on the number line. Therefore, we will be using negative 1 and positive 5. Since we have two zeros, the number line will have 3 intervals, namely numbers less than negative 1, numbers from negative 1 to 5, and numbers greater than 5. From these intervals, get a testing point. For example, in this interval, we will be getting negative 3. In the second interval, we will have 1. And for the third interval, we will have 7. Substitute these values to our given rational inequality and determine which among them will satisfy the given. So for example, for negative 3, remember that our given rational inequality is x plus 1 over x minus 5 is less than or equal to 0. If we will substitute negative 3 to the x of our given, then we will have negative 3 plus 1 over negative 3 minus 5 is less than or equal to 0. Simplifying this, we're gonna have negative 2 over negative 8 is less than or equal to 0. Negative 2 divided by negative 8 is equal to positive 1/4. Is less than or equal to 0. Notice that this statement is false because 1/4 is greater than 0. This time, we will be using positive 1. We will substitute positive 1 to our given rational inequality. If x is equal to 1, then our rational inequality will become 1 plus 1 over 1 minus 5 is less than or equal to 0. Simplifying this, we will have 2 over negative 4 is less than or equal to 0. And when we simplify 2 over negative 4, we will have negative 1/2 is less than or equal to 0. Notice that this statement is true because all negative numbers is less than 0. Finally, do the same thing to our last testing point. If x is equal to 7, then our rational inequality will become 7 plus 1 over 7 minus 5 is less than or equal to 0. 7 plus 1 equals 8 over 7 minus 5 equals 2 is less than or equal to 0. Simplifying 8 divided by 2 will give us 4 is less than or equal to 0. Looking at this statement, we know that this is false because 4 is greater than 0. From here, we can now say that the solution are the numbers from negative 1 to positive 5. Therefore, our rational inequality is being satisfied by the values on the second interval. However, note that 5 is not included in the solution set because it will make our denominator equal to 0. We will write our answer in this notation. X is greater than or equal to negative 1 but less than 5. This is read as x is greater than or equal to negative 1 but less than 5. Means that the values of x are between negative 1 and positive 5. And negative 1 is included. That is why we have equal sign here and we don't have equal sign here. So therefore, this is our final answer. Let us have another example. Solve the rational inequality x squared plus 4x plus 3 over x minus 1 is greater than 0. Again, determine first the zeros of the numerator and the denominator. But before that, let us factor the numerator before determining the zeros. Remember that the factors of x squared plus 4x plus 3 are x plus 3 and x plus 1. Let us equate both factors by 0. So we will have x plus 3 equals 0 and x plus 1 equals 0. Next, solve for x. Here, x is equal to negative 3 and here, x is equal to negative 1. Therefore, the zeros of the numerator are negative 3 and negative 1. The zero of the denominator is x minus 1 equals 0, so x equals 1. After determining the zeros, we will be using these values to determine the intervals in the number line. Since we have three zeros, namely -3, -1, and 1, the number line has four intervals. We have the numbers less than -3, the numbers from -3 to -1, the numbers from -1 to +1, and the numbers greater than 1. Select a testing point from each interval. Say we have, for the first interval, -5, for the second interval, -2, for the third interval, 0, and for the fourth interval, 3. Just like what we did on our first example, we will substitute these values to our given rational inequality and determine which among them will satisfy the given. Remember that our given is x squared plus 4x plus 3 over x minus 1 is greater than 0. For the first testing point, if x is equal to -5, then our given will become -5 squared plus 4 times -5 plus 3 all over -5 minus 1 is greater than 0. Simplifying this, we will have 25 minus 20 plus 3 all over -6 is greater than 0. 25 minus 20 is equal to 5 plus 3 equals 8. So we will have 8 over -6 is greater than 0. Simplifying this, we will have 4 or -4 over 3 is greater than 0. Notice that this statement is false because negative number is less than 0. Let us try our second testing point, which is -2. If x is equal to -2, then our rational inequality will become -2 quantity squared plus 4 times -2 plus 3 all over -2 minus 1 is greater than 0. Simplifying this, we will have 4 minus 8 plus 3 over -3 is greater than 0. Then we will have 4 minus 8 is -4 plus 3 is -1 over -3 is greater than 0. Simplifying this, we will have 1/3 is greater than 0. Notice that this statement is true because positive is greater than 0. For the next interval, we will be using 0. If x is equal to 0, then our rational inequality will become 0 squared plus 4 times 0 plus 3 all over 0 minus 1 is greater than 0. 0 squared is 0. 4 times 0 is 0 plus 3 over -1 is greater than 0. Simplifying this, we will have 0 plus 0 is 0 plus 3 is 3 over -1. 3 divided by -1 is equal to -3 greater than 0. However, negative is not greater than 0, so therefore, this is false. Finally, for our fourth testing point, if x is equal to 3, then our rational inequality will become 3 squared plus 4 times 3 plus 3 all over 3 3 minus 1 is greater than 0. 3 squared is 9. 4 times 3 is 12 plus 3 all over 2 is greater than 0. 9 plus 12 is 21 plus 3 is 24. 24 over 2 is greater than 0. 24 divided by 2 is 12, greater than 0. And note that this statement is true. Since the statement or our given rational inequality is true on these intervals, specifically from -3 to -1, and numbers which are greater than 1, then how are we going to write our solution set? In writing our solution set, note the intervals where our rational inequality became true. On this interval, our rational inequality became false when x equals -5. On this interval, our inequality became true when x equals -2. On this interval, our inequality became false. And finally, on this interval, our inequality became true. Therefore, our solution set for the rational inequality would be x is greater than -3 but less than -1 union with x greater than -3. Remember that this interval are the numbers between -3 and -1, and these numbers are greater than 3. So therefore, this is our final answer. I hope that you understood the lesson, and for the next video, we will discuss about the introduction of rational functions. Thank you so much and see you on the next discussion.
Good day, everyone. In this video, we will discuss about the domain and restrictions of rational functions. We have defined the rational function as a function of the form f of x equals p of x over q of x, where p of x and q of x are polynomial functions and q of x cannot be equal to 0. By the definition, it is very clear that the denominator cannot be equal to 0. Otherwise, the entire rational function will be undefined. Hence, there lies the restrictions of the rational function. The restrictions are the values of x that will make the denominator equal to 0. These are the steps in finding the domain or the restrictions of the rational function. First, factor the denominator. Second, equate the factors of the denominator to 0. And finally, solve for the restriction. Let us have an example. Determine the domain of the rational function f of x equals 1 over x minus 2. Notice that the rational function is already in its lowest term. Therefore, we cannot factor it anymore. To find the domain, let us determine the restriction by equating the denominator to 0. Hence, we will have x minus 2 equals 0. Then, x equals 2. Therefore, our restriction is x equals 2, meaning the value of x cannot be equal to 0, since this value will make our denominator equal to 0. Finally, to properly write our domain, we will have the domain is the set of values of x such that x is an element of real numbers except 2. Let us have another example. Determine the domain of the rational function f of x equals 2x over 3x plus 1. This given rational function is also in lowest term. Hence, we cannot factor it anymore. To find the domain, let us determine the restriction by equating the denominator to 0. Therefore, we will have 3x plus 1 equals 0. Isolate the constant term to the right side of the equation, giving us 3x equals negative 1. And to solve for the value of x, let us divide both sides by 3. Therefore, we will have x equals negative 1/3. Therefore, our restriction is x equals negative 1/3, meaning the value of x cannot be equal to negative 1/3 since this value of x will make the denominator equal to 0. And once again, to properly write our domain, we will have the set of values of x such that x is an element of real numbers except negative 1/3. Finally, for our last example, determine the domain of the rational function f of x equals x squared minus 4x plus 3 all over x squared minus 5x plus 4. In this given, observe that we can factor the denominator to be x minus 1 times x minus 4. Since we have two factors at the denominator, to find the restrictions, we will equate both factors to 0 and solve for the value of x. Therefore, we will have x minus 1 equals 0 and x minus 4 equals 0. On this factor, we will have x equals 1, and on this one, we will have x equals 4. Therefore, the restrictions are 1 and 4, since they will make the denominator equal to 0. Finally, to write our domain, we will have the set of values of x such that x is an element of real numbers except 1 and 4. I hope that you have understood the lesson. For our next video, we will discuss about the asymptotes of the rational functions. Thank you so much for listening and see you on our next discussion. Good day, everyone. In this video, we will discuss about asymptotes of rational functions. Let us define first what is an asymptote. Asymptote is a line or a curve that the graph of a function gets close to but does not touch. As for this video, we will discuss about vertical and horizontal asymptotes only. Vertical asymptote. The vertical line x equals a is a vertical asymptote of a function f if the graph of f either increases or decreases without bound as the x values approach a from the right or left. On the other hand, we also have the horizontal asymptote. The horizontal line y equals b is a horizontal asymptote of the function f if f of x gets closer to b as x increases or decreases without bound. The question is, how are we going to find the asymptotes? These are the steps in determining the vertical asymptotes. First, reduce the rational function to lowest terms by canceling out the common factor or factors in the numerator and denominator. Second, find the values a that will make the denominator of the reduced rational function equal to 0. And finally, the line x equals a is the vertical asymptote. On the other hand, to determine the horizontal asymptotes, we have the following steps. Let n be the degree of the numerator and m be the degree of the denominator. Remember that the degree is the highest exponent at the variable. If n is less than m, the horizontal asymptote is y equals 0. If n equals m, the horizontal asymptote is y equals a over b, where a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. And finally, if n is greater than m, there is no horizontal asymptote. Let us have some examples. For the first one, find all asymptotes of the graph of the rational function below. F of x equals 1 over x minus 2. Since the rational function is in lowest term, to find the vertical asymptote, set the denominator equal to 0 and solve for the value of x. Thus, we will have x minus 2 equals 0 and finally x equals 2. Thus, the graph has the line x equals 2 as its vertical asymptote. For the horizontal asymptote, notice that the degree of the numerator is less than the degree of the denominator. The degree of the numerator is 0 and the degree of the denominator is 1. Since n is less than m, therefore it satisfies the first condition that its horizontal asymptote is the line y equals 0. This is the graph of f of x equals 1 over x minus 2. And it shows its vertical asymptote to be x equals 2. And the horizontal asymptote y equals 0. It means that no matter how long the graph extends, it will never touch the lines x equals 2 and y equals 0. Let us have another example. Find all asymptotes of the graph of the rational function f of x equals 2x all over 3x plus 1. Once again, since the numerator and the denominator has no common factor, we just need to equate the denominator to 0 and solve for the value of x for us to be able to determine the vertical asymptote. Thus, we will have 3x plus 1 equals 0. 3x equals negative 1 as we isolate the constant term to the right side of the equation and divide both sides by 3. Therefore, we will have x equals negative 1/3. Therefore, x equals negative 1/3 is our vertical asymptote. On the other hand, notice that the highest exponent of the variable of the numerator is 1. So therefore, n is equal to 1. and the highest exponent at the denominator is also equal to 1. Hence, we can say that n is equal to m. And this satisfies the second condition. Therefore, the horizontal asymptote is the line represented by A over B, wherein A is the leading coefficient of the numerator and B is the leading coefficient of the denominator. Going back to our given, the leading coefficient of the numerator is 2, and the leading coefficient of the denominator is 3. Therefore, our horizontal asymptote will be y equals 2 over 3. This is the graph of f of x equals 2x all over 3x plus 1. It shows that the vertical and horizontal asymptotes are x equals negative 1/3 and y equals 2/3 respectively. Another example, find all asymptotes of the graph of the rational function f of x equals x squared over x plus 1. To determine the vertical asymptote, let us again equate the denominator by 0. So we will have x plus 1 equals 0, and then solve for x. So we will have x equals negative 1. So therefore, x equals negative 1 is our vertical asymptote. Moreover, for the horizontal asymptote, notice that the degree of the numerator is 2. So we can say that n is equal to 2. And the degree of the denominator is 1. So we can say that m equals 1. For this case, notice that n is greater than m. So it satisfies the third condition. The third condition states that if the degree of the numerator is greater than the degree of the denominator, then there is no horizontal asymptote. Therefore, the given function has no horizontal asymptote. This is the graph of the function f of x equals x squared all over x plus 1. The graph shows the vertical asymptote is x equals negative 1, and there is no horizontal asymptote. For our last example, find all asymptotes of the graph of the rational function f of x equals x squared minus 4x plus 3 all over x squared minus 5x plus 4. Here, notice that we can still factor the numerator and the denominator. Therefore, we will have x minus 1 quantity x minus 3 for our numerator and x minus 1 times x minus 4 for our denominator. If this is the case, then there is a common factor. It means that the graph has a whole. Since x minus 1 is the common factor, the whole is at x equals 1. Moreover, for the vertical asymptote, equate the remaining factor of the denominator to 0. So we will have x minus 4 equals 0 and solve for the value of x. Therefore, we will have x equals 4. Therefore, the vertical asymptote of our rational function is the line x equals 4. Going back to the given, notice that the highest exponents of the numerator and the denominator are equal, and they are both equal to 2. Hence, the horizontal asymptote of our rational function is the line y equals a over b, wherein a is the leading coefficient of the numerator and b is the leading coefficient of the denominator. the leading coefficient of the numerator is 1. And the leading coefficient of the denominator is also 1. Therefore, the horizontal asymptote is the line y equals 1. This is the graph of the rational function f of x equals x squared minus 4x plus 3 all over x squared minus 5x plus 4. Notice that it has a hole at x equals 1, and the vertical asymptote is x equals 4, while the horizontal asymptote is the line y equals 1. I hope that you have understood the lesson. For the next video, we will discuss about the zeros and intercepts of rational functions. Thank you for listening and see you on our next discussion. Good day, everyone. In this video, we will discuss about zeros and intercepts of rational functions. Remember that in a rational function, we always have a restriction that the denominator should not be equal to 0, since the division by 0 is undefined. Therefore, 5 over 0, 92 over 0, and negative 10 over 0 are all undefined. On the other hand, if the numerator is 0, then the rational expression will be 0, like 0 over 5, 0 over 92, and negative 0 over 10. Therefore, we define 0 of rational function as a value that will make the numerator equal to 0 without making the denominator equal to 0. Meaning, 0 or zeros of rational function are value or values of x that will make the numerator equal to 0, but it will not make the denominator equal to 0. These are the steps in finding the zeros of rational functions. First, if possible, factor the numerator and the denominator. Second, identify the restrictions of the denominator, values that will make the denominator equal to 0. Third, identify the values that will make the numerator equal to 0. And finally, determine the 0 or zeros of the rational function. Let us have an example. Find the zeros or 0 of the rational function below. We have f of x equals x squared plus 5x plus 6 all over x squared minus 4. First, let us factor the numerator and the denominator. When we factor the numerator and the denominator, we will have x plus 2 times x minus 3 to be the factors of x squared plus 5x plus 6, and for the denominator, the factors of x squared minus 4 are x plus 2 times x minus 2. Next, identify the restrictions of the denominator. So once again, the restrictions of the denominators are the values of x that will make the denominator equal to 0. So to do that, we simply equate the two factors by 0. So x plus 2 equals 0 and x minus 2 equals 0. So when we solve for the value of x, here we have x equals negative 2, and here we have x equals 2. Therefore, from here, we can say that x cannot be equal to negative 2 and 2, since they will make the denominator equal to 0. If the denominator becomes 0, then the whole rational function will be undefined. On the other hand, let us determine the values of x that will make the numerator equal to 0. So, what are we going to do is to equate the factors of the numerator to 0. So, we will have x plus 2 equals 0 and x minus 3 equals 0. So next, let us solve for the values of x. So x is equal to negative 2 and x is equal to positive 3. So from here, we can see that the values that will make the numerator equal to 0 are negative 2 and positive 3. Remember, the definition of 0 of a rational function are the values of x that will make the numerator equal to 0. However, if you will look at the value x equals negative 2, this value is also a restriction. For that case, this value is not a 0 of the rational function. Therefore, the 0 of the given rational function is x equals 3. Let us have another example. Find the 0 or zeros of the rational function below. F of x equals x squared minus 10x plus 25 all over x squared minus 25. Again, we factor first the numerator and the denominator. So we will have, for the numerator, the factors of x squared minus 10x plus 25 are x minus 5 and another x minus 5. All over, the factors of x squared minus 25 are x minus 5 times x plus 5. Next, let us determine the restrictions of the denominator. So once again, to determine the restrictions of the denominator, let us equate the two factors of the denominator to 0. So x minus 5 equals 0 and x plus 5 equals 0. So when we solve for the value of x, we have here x equals 5 and here x equals negative 5. Therefore, our restrictions would be x cannot be equal to negative 5 and positive 5 because these values will make our denominator 0 and will make the entire rational function undefined. Also, determine the values of x that will make the numerator equal to 0. So to do that, let us equate the factors of the numerator to 0. So we will have x minus 5 equals 0 and then x minus 5 equals 0. So here, when we solve for the value of x, we have x equals 5 and also on the other side, we have x equals 5. Since they are the same, we can simply write here x equals 5. Notice that x equals 5 as the 0 of the numerator is also a restriction at the denominator. So, since it is also a restriction, we cannot consider x equals 5 as a 0 of the rational function. Therefore, the rational function has no 0. Let us go to the intercepts of rational functions. When we say intercepts, these are the x and y coordinates of the points at which a graph crosses the x-axis or the y-axis respectively. Therefore, we have two intercepts, the x-intercept and the y-intercept. The x-intercept is the x-coordinate of the point where the graph crosses the x-axis, while the y-intercept is the y-coordinate of the point where the graph crosses the y-axis. These are the steps in finding the x and y-intercepts of the rational function. First, to find the x-intercept, substitute 0 for y and solve for x. And to find y-intercept, substitute 0 for x and solve for y. Let us take this example. Find the intercepts of the rational function below. F of x equals x plus 10 over x plus 2. To find the x-intercept, we need to set y equals 0.
So what we need to do is to substitute 0 to our f of x, because remember that f of x is equal to y. Hence, we will have 0 equals x plus 10 over x plus 2. Remember that since this is 0, when we cross multiply 0 times x plus 2, that will still be 0. So we will have 0 equals x plus 10. To solve for the value of x, isolate the constant to the left side of our equation. So we're gonna have x equals negative 10. Therefore, the x-intercept of the rational function is negative 10. For the y-intercept, we need to set the value of x be equal to 0. So we will have y equals 0 plus 10 all over 0 plus 2. So when we simplify, we will have 0 plus 10 will give us 10 over 0 plus 2 is 2. 10 divided by 2 is 5. Therefore, the y-intercept of our given is 5. Here is another example. Find the intercepts of the rational function below. F of x equals x squared plus 7x plus 10 all over x squared minus 5. Once again, to solve for the x-intercept, we need to set y to 0. So we will have 0 equals x squared plus 7x plus 10 all over x squared minus 5. Once again, when we do cross multiplication, we will have x squared plus 7x plus 10 equals 0. Since this is a quadratic equation, we need to factor the quadratic equation. The factors of x squared plus 7x plus 10 are x plus 2 times x plus 5. Next, let us equate both factors by 0. X plus 2 equals 0 and x plus 5 equals 0. Solve for the value of x. Here, this will give us x equals negative 2, and here, this will give us x equals negative 5. Therefore, we have here two x-intercepts. The x-intercepts are negative 2 and negative 5. On the other hand, to solve for the y-intercept, we need to set x to 0. So we will have y equals 0 squared plus 7 times 0 plus 10 all over 0 squared minus 5. Next, let us simplify the numerator and the denominator. 0 squared is equal to 0 plus 7 times 0 is also 0. So 0 plus 0 is 0 plus 10. That will give us 10 all over 0 squared is 0 minus 5 is negative 5. Simplify, 10 divided by negative 5 is negative 2. Therefore, the y-intercept is negative 2. Lastly, find the intercepts of the rational function below. F of x equals x squared plus 16 all over x squared minus 4. Once again, to solve for the x-intercept, set y be equal to 0. So we will have 0 equals x squared plus 16 all over x squared minus 4. So when we do cross multiplication here, it will give us x squared plus 16 equals 0. To solve for the value of x, isolate the constant to the right side, giving us with x squared equals negative 16. And to solve for the value of x, get the square root of both sides.
However, notice that we need to evaluate here square root of negative 16. And remember that a negative number does not have any real square root. Therefore, this function does not have x-intercept. How about the y-intercept? To solve for the y-intercept, set x be equal to 0. So we will have y equals 0 squared plus 16 all over 0 squared minus 4. So we will have y equals 0 squared is 0 plus 16, it will give us 16. All over 0 squared is 0 minus 4 is negative 4. Divide 16 by negative 4, it will give us negative 4. So therefore, the y-intercept is negative 4. I hope that you have understood the lesson. And for the next video, we will discuss about the inverse functions. Thank you and see you on our next discussion. Good day everyone! In this video, we will discuss about the introduction of inverse functions. We have defined before a relation to be a set of ordered pairs. Moreover, the set of the first coordinates or the x values is called the domain, and the set of the second coordinates or y values is called the range. Furthermore, we have also discussed about one-to-one correspondence and defined it to be a function in which for each value of y in the range of f, there is just one value of x in the domain of f such that y is equal to f of x. In this video, we will discuss about the inverse of a function. Inverse of a function. Reversing the domain and the range of a function will result to the inverse of the function. If f is a one-to-one function, then the inverse of f, denoted by f raised to negative 1, is the function formed by reversing all the ordered pairs in f. Thus, the inverse of a function is equal to y, x such that x, y is in f. With these definitions, the inverse of the function will have the following properties. Number 1, if the inverse of a function is 1-to-1, then the function is also 1-to-1. Number 2, the domain of the inverse of a function is equal to the range of the function. And finally, number 3, the range of the inverse of a function is equal to the domain of the function. Let us consider this example. Find the inverse of the function represented by the set of ordered pairs below. Remember that the inverse of the function is the reverse of the function in terms of the domain and the range. Meaning, to find the inverse of a function, we simply need to interchange the x value and the y value. So we will have 2, negative 1, negative 4, 3, negative 6, 5, 8, negative 7, and 10, negative 9. Therefore, the inverse of the given set of ordered pairs is 2, negative 1, negative 4, 3, negative 6, 5, 8, negative 7, and 10, negative 9. Going back to the given set of ordered pairs, the domain in this given set is the set of x values, which are -1, 3, 5, -7, and -9. And the range is the set of y values, such as 2, -4, -6, 8, and 10. On the other hand, the domain of the inverse is 2, -4, -6, 8, and 10. While the range is -1, 3, 5, -7, and -9. Notice that the domain of the function is equal to the range of the inverse. And the range of the function is equal to the domain of the inverse. Therefore, to find the inverse of a function given as a set of ordered pairs, we simply need to interchange the values of x and y. Let us have another one. Find the inverse of the function represented by the set of ordered pairs below. F is equal to the set of 11, -12, 13, -14, 15, -16, 17, -18, and 19, -20. Again, to solve for its inverse denoted by f raised to -1, what we need to do is simply interchange the values of x and y. So we will have the set of points -12, 11, -14, 13, -16, 15, -18, 17, and -20, 19. So this is the inverse of the given function. I hope that you have understood the lesson. For our next video, we will discuss about the inverse of one-to-one function. Thank you for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about the inverse of one-to-one function. In the previous video, we have discussed that to be able to determine the inverse of the function denoted by f raised to -1, we need to reverse the domain and the range of the given function. Also, the properties of an inverse of a function are the following. If the inverse of a function is 1-to-1, then the function is also 1-to-1. Second, the domain of the inverse of a function is equal to the range of the function. And finally, the range of the inverse of a function is equal to the domain of the function. Finally, we have also discussed on how to determine the inverse of a function given a set of ordered pairs. This time, let us discuss how to find the inverse of a function given the equation. These are the steps that we need to remember. First, we need to replace f of x with y. Next step, interchange x and y. Next, solve for the new y from the equation in step 2. And finally, replace the new y with inverse of f of x if the inverse is a function. Let us consider this example. Given f of x equals x plus 2, find the inverse of the function. Following the presented steps earlier, first, we need to express f of x to y. Therefore, we will have y equals x plus 2. Next step, interchange x and y. So we will make y as x and x as y. Therefore, it will become x equals y plus 2. After that, we need to solve for y in this new equation. To do that, we need to isolate y on one side of the equation. Since we have 2 here, we need to write 2 on the other side of the equation, giving us with x minus 2 equals y. By reflexive property, we can write this equation as y equals x minus 2. Finally, let us replace y with inverse of f of x. Therefore, the inverse of the given is x minus 2. Let us have another example. Given f of x equals 5x minus 7, find the inverse of the function. Again, for the first step, let us set f of x into y. So we will have y equals 5x minus 7. Next step, interchange y and x. So we will have x equals 5y minus 7. Next, solve for y in this new equation. So what we need to do first is to isolate the term with y on one side of our equation. Writing negative 7 on the other side of the equation, it will become positive 7. So we will have x plus 7 equals 5y. By reflexive property, we can write this equation as 5y equals x plus 7. Notice that we have a numerical coefficient on y not equal to 1. If this is the case, we need to divide the whole equation by that numerical coefficient. 5 divided by 5 is equal to 1. So therefore, we will have y equals x plus 7 over 5. Finally, set y as the inverse of the function. So the inverse of the function is x plus 7 all over 5. For our last example, given f of x is equal to 5x minus 3 all over 7, let us find the inverse of the function. So once again, let us set f of x to y. Y equals 5x minus 3 all over 7. Next, interchange y and x. So we will have x equals 5y minus 3 all over 7. From here, we need to solve for y in this new equation. But since we have a denominator here, we need to eliminate the denominator by multiplying the whole equation by it. So we will have 7x equals 5y minus 3. Next, let us isolate the term with y. So let us write negative 3 on the other side of the equation, giving us with 7x plus 3 equals 5y. Once again, by reflexive property, we can write the equation 5y equals 7x plus 3. Since the numerical coefficient of y is not equal to 1, we need to eliminate it by dividing the whole equation by that numerical coefficient. So we need to divide both sides of the equation by 5. So 5 divided by 5 is equal to 1. So we will have y equals 7x plus 3 all over 5. Finally, write y as inverse of the function. So the inverse of the function f of x is equal to 7x plus 3 all over 5. Note that given a function and its inverse, the following property is applicable. If g of x is an inverse of f of x, then f of g of x is equal to x and g of f of x is equal to x. Meaning, if we will solve for the compositions of the function and its inverse, then the result is both equal to x. We can use this property in verifying if two functions are inverses of each other. For example, solve that the given functions are inverses of each other. F of x is equal to x minus 3 and g of x is equal to x plus 3. To determine that they are inverses of each other, then we need to verify that f of g of x is equal to x and g of f of x is also equal to x. To do that, we need to recall the steps in doing composition of functions. For f of g of x, we need to substitute the entire g of x to the x of f of x. Hence, we will have x plus 3 minus 3. Simplifying this, it will give us x plus 3 minus 3. Finally, positive 3 minus 3 is equal to 0. So we will have here x. Therefore, we can easily see that f of g of x is equal to x. So the first one is being satisfied. For the second one, g of f of x, what we need to do is to substitute f of x to the x of g of x. So we will have x minus 3 plus 3. Simplifying this, we will have x minus 3 plus 3 and negative 3 plus 3 is 0. So finally, we will have here x. So once again, g of f of x is also equal to x. Since both of the compositions of functions were being satisfied, then we can say that f of x and g of x are inverses of each other. Let us have another example. Show that the given functions are inverses of each other. Given that f of x is equal to 3x plus 5 and g of x is equal to x minus 5 over 3. So once again, we need to satisfy that f of g of x is equal to x and g of f of x is also equal to x. So therefore, for the first one, f of g of x, what we need to do is to substitute g of x to the x of f of x. So we will have 3 times x minus 5 all over 3 plus 5. Here, since we multiply 3 on an expression with the denominator of 3, we can cancel this out since this will become equal to 1. So we will have x minus 5 plus 5. Simplifying x minus 5 plus 5, it will give us x. So therefore, f of g of x is equal to x. The first condition is being satisfied. On the other hand, g of f of x, we need to substitute the entire f of x to the x of g of x. So we're gonna have 3x plus 5 minus 5 all over 3. Simplifying the numerator, positive 5 minus 5 is 0. So we will have 3x divided by 3. And 3 divided by 3 is equal to 1. So we have here x. So therefore, g of f of x is equal to x. With this, both the conditions were being satisfied. Therefore, f of x and g of x are inverses of each other. I hope that you have understood the lesson. For the next video, we will discuss about the graphs of inverse functions. Thank you for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about the graphs of inverse functions. The graph of the inverse is the reflection of the graph of the original function. The axis of symmetry is the line y equals x. Considering this example, graph the function below and its inverse. What we need to do first is to determine the inverse of the given set of ordered pairs. Remember that in determining the inverse of a function given in a set of ordered pairs, we simply need to interchange the values of x and y. Therefore, the inverse will be the set of points 1, 0, 3, 1, 5, 2, 7, 3, 9, 4, and 11, 5. To graph the function and its inverse, we will plot the ordered pairs in a Cartesian plane and connect all the points. This is the graph of the original function with ordered pairs 0, 1, 1, 3, 2, 5, 3, 7, 4, 9, and 5, 11. On the other hand, this is the graph of the inverse of the original function with ordered pairs 1, 0, 3, 1, 5, 2, 7, 3, 9, 4, and 11, 5. Notice that the graph of the inverse is actually a mirror image of the original function with respect to the line y is equal to x. Let us consider this example. Graph the function below and its inverse. We have the given function to be f of x equals 2x minus 3. Before graphing this function, let us first determine the inverse. Recall the steps in determining the inverse of a function. First, we need to express f of x by y. Next step, interchange y and x. So we will have x equals 2y minus 3. Next, isolate the term with y on one side of the equation. With that, we need to write negative 3 on the other side of the equation, making it x plus 3 equals to y. By reflective property, we can write the equation as 2y equals x plus 3. Next, divide both sides by 2 because the numerical coefficient of y should be equal to 1. So 2 divided by 2 is equal to 1. So we will have y equals x plus 3 over 2. Finally, change y into the inverse of f of x. Therefore, we need to graph the given function f of x and its inverse x plus 3 all over 2. This is the graph of f of x is equal to 2x minus 3 with points 2, 1, 4, 5, 5, 7, and 7, 11. This is the graph of the inverse of f of x, which is equal to x plus 3 all over 2 with coordinates 1, 2, 3, 3, 5, 4, 7, 5, 9, 6, and 11, 7. Notice that the two graphs are mirror images of each other with respect to the line y equals x. I hope that you have understood the lesson. For the next video, we will discuss about the exponential functions. Thank you for listening and see you on our next discussion.
Good day everyone! In this video, we will discuss about exponential functions, equations, and inequalities. By definition, exponential expression is an expression of the form a times b raised to x minus c plus d, where b is greater than 0 and b should not be equal to 1. Notice that in an exponential expression, the exponent has an independent variable x. Therefore, for an expression to be an exponential expression, the exponent should have an independent variable x. Moreover, exponential equation is an equation that involves exponential expressions. For example, 7 raised to 2x equals 4. In here, to determine that it is an exponential equation, you need to look at the exponential expression and the equal sign. Furthermore, exponential inequality is an inequality that involves exponential expressions. For example, 5 raised to x plus 4 is greater than or equal to 10. Therefore, to determine that it is an exponential inequality, you need to note that there should be an exponential expression and an inequality symbol. Remember that our inequality symbols are greater than, less than, greater than or equal to, and less than or equal to. Finally, an exponential function can be written as f of x is equal to b raised to x, where b should be greater than 0 and b should not be equal to 1. Also, x is any real number. Therefore, to determine that it is an exponential function, note of the exponential expression and an f of x or y. Let us try to determine whether the given is an exponential function, an exponential equation, an exponential expression, or none of these. For the first one, we have 3 quantity 5 raised to x plus 1 equals 300. Looking at the given, notice this exponential expression with an equal sign. Therefore, this is an exponential equation. On the second given, y equals 4 raised to x plus 7, note that we have the dependent variable y which is equal to f of x and an exponential expression. Therefore, this is an exponential function. Finally, on our third example,
f of x equals 5x squared. Looking at the exponent, since it does not have an independent variable x, it means that this is not an exponential expression. Therefore, it cannot be an exponential function, exponential equation, or exponential inequality. Therefore, the answer is none of these. With this, here are the concepts that we have discussed in this video. Exponential expression is an expression of the form a times b raised to x minus c plus d. Exponential equation is an equation that involves exponential expressions. Exponential inequality are inequalities that involve exponential expressions. And finally, an exponential function is a function that can be written as f of x equals b raised to x. I hope that you have understood the lesson. For the next video, we will discuss about exponential functions. Thank you for listening and see you on our next discussion.
Good day everyone! In this video, we will discuss about exponential functions. We have defined an exponential function to be a function that can be written as f of x equals b raised to x, where b is greater than 0, b should not be equal to 1, and x is any real number. From the definition, note that b is a constant value and it is called as base. The exponent of an exponential function is an independent variable x that can be any real number. F of x equals 5 raised to x is an example of an exponential function where the base is 5 and the exponent is x. F of x equals 7 raised to x plus 3 is also an example of exponential function with base 7 and exponent of x plus 3 where the independent variable x is present. F of x equals x cubed is not an example of exponential function since the base is not constant, instead a variable x. Also, its exponent does not have the independent variable x, instead a constant 3. Likewise, f of x equals 1 raised to x is not an example of exponential function, even though its exponent is an independent variable x because the base cannot be equal to 1. Remember, from the definition of the exponential function, it was stated that b cannot be equal to 1 because when we raise 1 by any exponent, the value will always be equal to 1. Finally, the function f of x equals x raised to x is not an exponential function because both the base and the exponent are variables. Let us try to determine whether each function represents an exponential function or not. For the first given, we have f of x equals 10 raised to 2x plus 3. Notice that the expression 10 raised to 2x plus 3 has a constant base and its exponent has an independent variable x. Thus, this function is an exponential function. For the second one, f of x equals 15x raised to 2 plus x. Observe that the base has a variable x, aside from its constant 15. Therefore, this given does not represent an exponential function. Finally, for our last example, f of x equals 1/2 raised to x, see that the base is a constant value and the exponent is an independent variable x. Hence, this function represents an exponential function. Let us now discuss the graph of an exponential function. In graphing such function, it will be very helpful to make a table of values and plot the resulting points on a Cartesian plane. For an instance, consider the exponential function f of x equals 2 raised to x. Given some values of x, let us solve for the values of f of x or y. When x is equal to -3, then f of x will be equal to 2 raised to -3, which will result to 1/8. When x is equal to -2, then we will have 2 raised to -2, which will result to 1/4. When x is equal to -1, we will have 2 raised to -1, which will be equal to 1/2. 2 raised to 0 is equal to 1, 2 raised to 1 is equal to 2, 2 raised to 2 is equal to 4, and 2 raised to 3 is equal to 8. With this table of values, we can see that we have the following points: -3, 1/8, -2, 1/4, -1, 1/2, 0, 1, 1, 2, 2, 4, and 3, 8. Plotting these points on a Cartesian plane and connecting them, we have this graph as the graph of the given function f of x equals 2 raised to x. This time, let us graph the exponential function f of x equals 1/2 raised to x. Once again, given some values of x, let us solve for the values of f of x or y. When x is equal to -3, then f of x will be equal to 1/2 raised to -3, which is equal to 8. When x is equal to -2, then we will have 1/2 raised to -2, which will result to 4. When x is equal to -1, we will have 1/2 raised to -1, which will result to 2. 1/2 raised to 0 is equal to 1. 1/2 raised to 1 is equal to 1/2. 1/2 raised to 2 is equal to 1/4. And 1/2 raised to 3 is equal to 1/8. With this table of values, we can see that we have the points -3, 8, -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, and 3, 1/8. Plotting these points on a Cartesian plane and connecting them, we have this graph as the graph of the given function f of x equals 1/2 raised to x. Comparing the graphs of the two given exponential functions, f of x equals 2 raised to x and f of x equals 1/2 raised to x, we can observe the following. The values of x or the domain of the exponential functions can be any real number, while the values of y or the range are positive real numbers. Moreover, the graph of f of x equals 2 raised to x, where b or the base is greater than 1, shows an increasing trend. On the other hand, the graph of f of x equals 1/2 raised to x, where b is greater than 0 but less than -1, shows a decreasing trend. Additionally, both functions pass through the point 0, 1, since any number, when you raise it by 0, the value is always 1. Finally, observe that both graphs approaches the x-axis but never touches. Therefore, we can say that the given exponential functions are asymptotic to x-axis or the line y equals 0. With these observations, we can now conclude the properties of exponential functions and their graphs. Let f of x equals b raised to x, where b is greater than 0 and b is not equal to 1, the domain of the exponential function is the set of any real number. The range of the exponential function is the set of numbers greater than 0. If the base is greater than 1, then the function is increasing, while if the base is greater than 0 but less than 1, then the function is decreasing. The function passes through 0, 1 since f of 0 is equal to b raised to 0, which is equal to 1. And finally, the graph is asymptotic to x-axis. I hope that you have understood the lesson. For the next video, we will discuss about transformations of the graphs of exponential functions. Thank you for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about the transformations of the graphs of exponential functions. We have defined exponential function as a function that can be written in the form f of x equals b raised to x, where b is greater than 0, b is not equal to 1, and x is any real number. Moreover, we have also discussed the properties of the exponential functions and their graphs, and these are the following. Let f of x be equal to b raised to x, where b is greater than 0 and b is not equal to 1. Domain is the set of values of x, wherein x is an element of real numbers. Range is the set of values for y, where y is greater than 0. If b is greater than 1, then f is increasing. If b is greater than 0 but less than 1, then f is decreasing. The function passes through the point 0, 1, since f of 0 is equal to b raised to 0, which is equal to 1. The graph is asymptotic to x-axis. To discuss the transformations of the graphs of exponential functions, we will use the function f of x equals 2 raised to x as our mother function, and we will compare graphs of other exponential functions from this graph. Recall that we have also discussed that in graphing exponential functions, it will be a great help if you will make a table of values and plot the resulting ordered pairs on a Cartesian plane. The graph shows 3 exponential functions. The red one is the graph of the mother function f of x equals 2 raised to x. Moreover, the blue one is the graph of f of x equals to quantity 2 raised to x. Comparing it to the mother function, it is vertically stretched. On the other hand, the green one is the graph of f of x equals 1/2 quantity 2 raised to x. And comparing it again to the graph of f of x equals 2 raised to x, it is vertically shrink. From the previous illustration, we can conclude that when exponential function f of x equals b raised to x is being multiplied to a constant c, the graph will either vertically stretched or vertically shrink. Vertically stretching will happen if the multiplier c is greater than 1. On the other hand, vertically shrinking will happen if the multiplier c is greater than 0 but less than 1. On this one, the illustration shows graphs of three exponential functions. Again, the red graph represents f of x equals 2 raised to x. The blue one is the graph of f of x is equal to 2 raised to x plus 2. Notice the difference between the two functions. In the new function, we have added 2 in the exponent, and the graph translated to the left by 2 units as well. Moreover, the green graph represents f of x equals 2 raised to x minus 2. Comparing this graph from the red one, this graph was translated 2 units to the right when we have subtracted 2 in the exponent. What happened to the graphs earlier is called horizontal translation. It means shifting to the right or to the left. This happens when we add a constant c to the exponent. The graph shifts to the right when c is less than 0 and shifts to the left when c is greater than 0. In this illustration, the blue graph represents f of x equals 2 raised to x plus 2. And notice that from the graph of f of x equals 2 raised to x, it was shifted 2 units upward when we added 2 on the function. Likewise, the green graph represents the function f of x equals 2 raised to x minus 2, which was shifted 2 units downward from the graph of f of x equals 2 raised to x when we subtracted 2 from the function. What happened to the graphs earlier is called vertical translation. It means shifting upward or downward. This happens when we add a constant c to the function. The graph shifts upward when c is greater than 0 and shifts downward when c is less than 0. In this illustration, the blue graph represents the function f of x is equal to 2 raised to negative x. See that the graph of f of x equals 2 raised to x was reflected with respect to y-axis when the exponent was negated. On the other hand, the green represents the function f of x equals negative 2 raised to x, which is a reflected image of f of x equals 2 raised to x when the base was negated. The transformation happened to the graphs earlier is called reflections. This happens when the base or the exponent was negated. When the base is negated, then the reflection is about the x-axis. But when the exponent was negated, the reflection is about the y-axis. I hope that you have understood the lesson. For the next video, we will discuss about the domain and range of exponential functions. Thank you for listening and see you on our next discussion.
Good day everyone! In this video, we will discuss about solving exponential equations. Recall that an exponential equation is an equation that involves exponential expression. Means that an independent variable x is present on the exponent. In solving exponential equation, it is very important to note the one-to-one property. If x sub 1 is not equal to x sub 2, then it follows that b raised to x sub 1 is not equal to b raised to x sub 2. Conversely, if b raised to x sub 1 is equal to b raised to x sub 2, then x sub 1 is equal to x sub 2. The second sentence means that if there are two exponential expressions and their bases are equal, then it means that their exponents are also equal. Therefore, in solving exponential equations, to use the one-to-one property, we need to make sure that the bases on both sides of the equation are equal. Let us consider this example. Solve the exponential equation 5 raised to x equals 625. To solve this problem, note that our goal is to have same bases on both sides of the equation for us to use the one-to-one property. Looking at the bases of our given, notice that they are not equal. We have 5 as base on the left side and 625 on the right side. However, remember that we can actually write 625 with base of 5. Using exponents and base 5, we can express 625 by 5 raised to 4 because when we multiply 5 4 times to itself, the answer will be 625. From here, you can see that our bases now are the same. So therefore, we can apply the one-to-one property. So we can say that our exponents are equal. So therefore, x equals 4. Let us take this another example. Solve the exponential equation 4 raised to x plus 1 equals 64. Again, from the given, notice that they are not equal. We have here 4 and we have here 64. Recalling the exponents and bases, remember that 64 can be written with base of 4. It will be 4 raised to 3 because when we multiply 4 to itself 3 times, then the answer will be 64. Since the bases now here are the same, then we can apply the one-to-one property and equate the two exponents. So we will have x plus 1 equals 3. In solving the value of x, we need to isolate the x on the left side of the equation by subtracting 1 on both sides of our equation. Therefore, we will have x equals 3 minus 1, and simplifying the right side, it will give us x equals 2. Therefore, the value of x is 2. For our last example, solve the exponential equation 9 raised to 2x minus 6 equals 1/3 raised to 8x. In this given, we can actually express 9 and 1/3 with base of 3. Remember that 9 is equal to 3 raised to 2. Moreover, since 1/3 is a reciprocal of 3, therefore, its exponent will be -1. So our expression will be 3 squared raised to 2x minus 6 equals 3 raised to -1 raised to 8x. Notice from here that 9 became 3 squared and 1/3 became 3 raised to -1. Since we have here exponent raised by another exponent, remember to apply the power rule. Remember that power rule states that if a power is raised by another power, then we need to multiply the two exponents. So here, we need to multiply 2 times 2x minus 6, and here, we need to multiply -1 times 8x. Therefore, we will have 3 raised to 4x minus 12 equals 3 raised to -8x. From here, notice that we now have same bases, so we can equate the two exponents. So we will have 4x minus 12 equals -8x. In solving for the value of x, we need to combine like terms. So we will be writing negative 8x on the left side and negative 12 on the right side, resulting with 4x plus 8x equals 12. 4x plus 8x is equal to 12x, and copy equals 12. To solve for the value of x, we need to divide both sides of the equation by 12. So therefore, the value of x will be 1. I hope that you have understood the lesson. For the next video, we will discuss about solving exponential inequalities. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about solving exponential inequalities. Recall that an exponential inequality is an inequality that involves exponential expression, meaning for an expression to be an exponential inequality, then a variable should be present on the exponent and an inequality symbol is being used. Recall that our inequality symbols are greater than, less than, greater than or equal to, and less than or equal to. In solving exponential inequality, remember these properties. If b is greater than 1, then the exponential function y equals b raised to x is increasing for all x. This means that b raised to x sub 1 greater than b raised to x sub 2 if and only if x sub 1 is greater than x sub 2. Another one, if b is greater than 0 but less than 1, then the exponential function y equals b raised to x is decreasing for all x. This means that b raised to x sub 1 greater than b raised to x sub 2 if and only if x sub 1 is less than x sub 2. Therefore, if we are dealing with exponential inequality, we should always consider the value of b before applying the one-to-one property. If b is greater than 1 and b raised to x sub 1 is greater than b raised to x sub 2, then it follows that x sub 1 is also greater than x sub 2. But if the value of b is greater than 0 but less than 1, then it follows that if b raised to x sub 1 is greater than b raised to x sub 2, then it means that x sub 1 will be less than x sub 2. Let us take an example. Solve the exponential inequality 3 raised to x plus 1 is less than 9 raised to x minus 2. From the given, notice that the bases are not equal. However, remember that 9 can be expressed with base of 3 because 9 is equal to 3 squared. So therefore, we will have 3 raised to x plus 1 is less than 3 squared raised to x minus 2. Since we have here power raised by another power, then we need to multiply the two exponents. So we will have 3 raised to x plus 1 is less than 3 raised to 2x minus 4. Since we now have the same bases and the base is greater than 1, then it follows that the exponents will follow the same inequality symbol. So we're gonna have x plus 1 is less than 2x minus 4. Solving for the value of x, we need to combine like terms. So we will have x minus 2x is less than negative 1 minus 4. Simplify the left side of the inequality and also the right side of our inequality. Then we will have negative x is less than negative 5. Dividing both sides by negative 1, remember that the rule in inequality, if you are dividing both sides of the equation by a negative number, you need to change the inequality symbol. Therefore, less than will become greater than. Finally, the values of x should be greater than 5. Let us take another example. Solve the exponential inequality 4 raised to 2x plus 7 is less than or equal to 32 raised to 2x minus 3. From the given, notice that we have different bases. Therefore, we need to write them using the same bases. Since we cannot express 32 with base of 4, it means that we need to change the two bases. Remember that 4 and 32 can be expressed with base of 2. 4 is equal to 2 squared and 32 is equal to 2 raised to 5. Therefore, our expression will be 2 squared raised to 2x plus 7 is less than or equal to 2 raised to 5 raised to 2x minus 3. Again, by applying the power rule, we need to multiply the exponents 2 times 2x plus 7 and 5 times 2x minus 3. So we will have 2 raised to 4x plus 14 is less than or equal to 2 raised to 10x minus 15. Since the bases now here are the same, then we can apply the one-to-one property. Moreover, since the value of the base is greater than 1, we will still be following the same inequality symbol. Therefore, we will have 4x plus 14 is less than or equal to 10x minus 15. In solving for the value of x, we need to combine similar terms. So we will have 4x minus 10x is less than or equal to negative 14 minus 15. Simplifying the left side and the right side, we will have negative 6x is less than or equal to negative 29. Again, to solve for the value of x, we need to divide both sides by negative 6. But since our divisor is again a negative number, we need to change the inequality symbol. Remember that it only happens when we divide both sides of the equation by a negative number. If it is a positive number, then you do not need to change the inequality symbol. So in this case, since we have negative 6 as our divisor, then less than or equal to will become greater than or equal to. Finally, the value of x is greater than or equal to 29 over 6. I hope that you have understood the lesson. For our next video, we will discuss about solving problems involving exponential functions. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about applications of exponential functions. One application of exponential function is the exponential growth. The rule for exponential growth can be modeled by y is equal to ab raised to x, where a is the starting number, b is the growth factor, which is equal to 1 plus r, where r is the rate of growth, and x is the number of intervals like minutes, years, and so on. Let us have this example. A bacteria grows at a rate of 25% each day. There are 500 bacteria today. How many will there be tomorrow? And how many will there be 1 week from now? Based on the problem, we have the following given. There are 500 bacteria today. So therefore, A, or the starting number, is equal to 500. The rate of growth is equal to 25%. Therefore, B, which is equal to 1 plus R, will be equal to 1 plus 0.25 or 1.25. Moreover, since we were asked of how many bacteria will there be tomorrow, it means that our x is equal to 1. Substituting the values of a, b, and x on our formula y equals ab raised to x, we will have y equals 500 times 1.25 raised to 1. Remember that 1.25 raised to 1 is equal to 125. So it would be the same multiplying 1.25 by 500. Therefore, we will have y equals 625. Thus, there will be 625 bacteria tomorrow. On the other hand, 1 week from now means x will be equal to 7 because in a week, there is 7 days. Substituting again a, b, and x on our formula y equals ab raised to x, we will have y equals 500 times 1.25 raised to 7. When we multiply this, we will have 2,384.19. But since we were asked of how many bacteria, there is no 0.19 bacteria. Therefore, there will be 2,384 bacteria 1 week from now. Compound interest is the another application of exponential function. If P in pesos is deposited in an account and interest is paid K times a year at an annual rate R, the amount A in the account after T years is given by A equals P times 1 plus R over K raised to KT. Let us take a look at this example. To save for college, parents invest 12,000 pesos for their newborn child in a mutual fund that should average 10% annual return. If the quarterly interest is reinvested, how much will be available in 18 years? In this problem, take note of the following given. The amount invested is 12,000. Therefore, P is equal to 12,000. Moreover, the annual return is given to be 10%. Therefore, R is equal to 0.10. Since the interest is being on a quarterly basis, it follows that K is equal to 4 because in a year, there is 4 quarters. Moreover, since we were asked of how much will be available in 18 years, it follows that T is equal to 18. We will now substitute P, R, K, and T on our formula A equals P quantity 1 plus R over K raised to KT. Then we will have 12,000 quantity 1 plus 0.10 over 4 raised to 4 times 18. In this formula, we need to evaluate first 0.10 divided by 4 and 4 times 18. It will give us 0.025 for 0.10 divided by 4 and 72 for 4 times 18. Next step, let us add 1 and 0.025. Then we will have 12,000 times 1.025 raised to 72. Furthermore, simplifying the expression, we will have A equals 71,006.74. Therefore, in 18 years, the account will be worth 71,006.74. I hope that you have understood the lesson. For the next video, we will discuss about the introduction to logarithms. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about introduction to logarithm. What is logarithm? Let b, x, and y be positive real integers such that b is not equal to 1. The logarithm of y with base b is denoted by logarithm of y to the base b and is defined as x is equal to logarithm of y to the base b if and only if y is equal to b raised to x. With this definition, we need to remember the following. First, in both logarithmic and exponential forms, b is the base. In the exponential form, c is an exponent. This implies that the logarithm is actually an exponent. Thus, exponential and logarithmic functions are inverses. Second, when you were asked of what is the logarithm of, it is the same being asked what is the exponent of. Therefore, we need to study now the exponential and the logarithmic form. Remember, the exponential form is given by b raised to x is equal to y. And the logarithmic form is given by logarithm of y to the base b equals x. Having these two forms, notice that base would be written as subscript of the logarithm. The exponent x will be written on the other side of the equation, and the power y will be together with the logarithmic expression. Let us have some example. Rewrite each expression in logarithmic form. Number 1, 5 raised to 4 is equal to 625. And number 2, 1/2 cube equals 1/8. For the first given, 5 raised to 4 equals 625, notice that the base is 5, the exponent is 4, and the power is 625. With this, it follows that b is 5, x is 4, and y is 625. Remember that the logarithmic form is given as x equals logarithm of y to the base b. Hence, we need to substitute 4 to x, 5 to b, and 625 to y. It will now give us 4 equals logarithm of 625 to the base 5. On the second given, we have 1/2 as our base, 3 being the exponent, and 1/8 being the power. Then it implies that b is equal to 1/2, x is equal to 3, and y is equal to 1/8. Again, the logarithmic form is x equals logarithm of y to the base b. Thus, we need to substitute 3 to x, 1/2 to b, and 1/8 to y. It will result to the logarithmic form 3 equals logarithm of 1/8 to the base 1/2. Moreover, common logarithm is a logarithm with base 10. If a logarithmic expression has base 10, we usually do not write its base. Thus, if we have logarithm of x to the base 10, then it can be written as logarithm of x. Note that if you do not see any base in a logarithmic expression, it doesn't mean that the base is 0. It is automatically base is equal to 10 and the logarithmic expression is a common logarithm. Moreover, natural logarithm is a logarithm with base e. E is a natural number which is approximately equal to 2.71828. If a logarithmic expression has base e, we usually do not write its base, and we denote it by ln. Thus, if we have logarithm of x to the base e, then we can write it as ln of x. Let us have these examples. Rewrite each expression in exponential form. The first given is logarithm of 100 equals 2, and the second one is ln of e equals 1. For the first given, notice that since we do not have a base here, it means that this is a common logarithm with base 10, meaning b or our base is equal to 10. Also, we have x equals 2 and y equals 100. Recall that the exponential form is given by b raised to x is equal to y. Substituting b, x, and y to this exponential form, we will have 10 raised to 2 equals 100. On the second given, ln of e equals 1, notice that since we have ln here, it means that the given is a natural logarithm with base e. Therefore, it only follows that our base is equal to the natural number e. Going back to the given, we also have x equals 1 and y equals e. Therefore, if we will substitute b, x, and y to the exponential form b raised to x equals y, we will have e raised to 1 is equal to e. With the definition of the logarithm, we can now solve or evaluate simple logarithmic expressions. Let us consider these examples. For the first one, evaluate logarithm of 25 to the base 5 plus logarithm of 8 to the base 2. For the second one, logarithm of 1/64 to the base 1/2 minus logarithm of 27 to the base 3. For the first one, logarithm of 25 to the base 5 plus logarithm of 8 to the base 2. Looking at the first term, remember that when you were asked of what is the logarithm of, it is the same being asked what is the exponent of. Meaning, imagine that you were asked of what should be the exponent of 5 to have 25. With that, you may recall that 5 raised to 2 is actually equal to 25. Therefore, this would imply that logarithm of 25 to the base 5 is actually equal to 2. It means that for us to have 25, the base 5 should have an exponent of 2. On our second term, logarithm of 8 to the base 2, we were asked of what should be the exponent of 2 to become 8. Therefore, you may recall that 2 raised to 3 is equal to 8. Therefore, it only follows that logarithm of 8 to the base 2 is actually equal to 3. With this, The expression logarithm of 25 to the base 5 plus logarithm of 8 to the base 2 is actually equal to 2 plus 3. Simplifying 2 plus 3, we will have 5. Therefore, the expression logarithm of 25 to the base 5 plus logarithm of 8 to the base 2 is actually equal to 5. Moving to the next given, logarithm of 1 over 64 to the base 1/2 minus logarithm of 27 to the base 3. Again, for the first term, we were asked of what should be the exponent of 1/2 to be 1 over 64. So you may recall that 1/2 raised to 6 is equal to 1 over 64. Therefore, the logarithm of 1 over 64 to the base 1/2 is equal to 6. On the other hand, on the second term, logarithm of 27 to the base 3, we were asked of what should be the exponent of 3 to become 27. So you may recall that 3 raised to 3 is equal to 27. Thus, logarithm of 27 to the base 3 is equal to 3. With the values of 6 and 3, we can now equate the expression by 6 minus 3. Simplifying 6 minus 3, it will give us 3. Therefore, the expression logarithm of 1 over 64 to the base 1/2 minus logarithm of 27 to the base 3 is equal to 3. I hope that you have understood the lesson. For the next video, we will discuss about applications of logarithm. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about applications of logarithm. One application of logarithm is the sound intensity. In acoustics, the decibel level of a sound is denoted by D equals 10 logarithm of I over 10 raised to negative 12, where I is the sound intensity in watts per meter squared. Note that the quantity 10 raised to negative 12 watts per meter squared is the least audible sound a human can hear. Let us consider this example. The decibel level of sound in a quiet office is 10 raised to negative 6 watts per meter squared. What is the corresponding sound intensity in decibels? From the problem, it was given that the intensity is equal to 10 raised to negative 6 watts per meter squared. Substituting this given to our formula, D equals 10 logarithm of I over 10 raised to negative 12, we will have 10 logarithm of 10 raised to negative 6 over 10 raised to negative 12. Simplifying the exponents negative 6 and negative 12, we will have 10 logarithm of 10 raised to negative 6 minus negative 12. Thus, this expression will actually give us negative 6 plus 12. Simplifying negative 6 plus 12, we will have 10 logarithm of 10 raised to 6. Looking at this expression, recall that logarithm of 10 raised to 6 is actually a common logarithm with base 10. Therefore, evaluating this expression, we will have logarithm of 10 raised to 6 is actually equal to logarithm of 1 million to the base 10. Looking for the exact value of this expression, recall that when you were asked of what is the logarithm of is the same being asked what is the exponent of, meaning what should be the exponent of 10 to become 1 million. Therefore, we will have logarithm of 10 raised to 6 is equal to 6. This means that we need to multiply 10 6 times to itself to become 1 million. Since we have established that logarithm of 10 raised to 6 is equal to 6, we can actually substitute 6 in this expression, giving us with 10 times 6. Simplifying this, we're gonna have D equals 60. Therefore, the corresponding sound intensity in decibels is 60. Another application of logarithm is the acidity and the pH scale. The pH level of a water-based solution is defined as pH is equal to negative logarithm of H, where H is the concentration of hydrogen ions in moles per liter. Note that solutions with a pH of 7 are defined neutral. Those with pH less than 7 are acidic, and those with pH greater than 7 are basic. Considering this example, a 1 liter solution contains 0.00001 moles of hydrogen ions. Find its pH level. From the problem, it was given that H is equal to 0.00001, which is equal to 10 raised to negative 6. Substituting the given H to our formula, we're gonna have pH is equal to negative logarithm of 10 raised to negative 6. Looking at this expression, recall that this logarithmic expression is a common logarithm with base 10. Logarithm of 10 raised to negative 6 is equal to logarithm of 0.00001 to the base 10. The question would be, what is the exponent of 10 to become 0.00001? From here, we can see that logarithm of 10 raised to negative 6 is equal to negative 6. Therefore, establishing that this expression is actually equal to negative 6, we can substitute negative 6 to this expression, giving us with negative times negative 6, which is equal to positive 6. Therefore, the pH level of the 1 liter solution that contains 0.00001 moles of hydrogen ions is 6. I hope that you have understood the lesson. For our next video, we will discuss about properties of logarithms. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about the properties of logarithms. These are the properties of logarithm. For b not be equal to 1 and b should be greater than 0 and m and n are elements of real numbers, the first property states that the logarithm of m to the base b plus the logarithm of n to the base b is equal to logarithm of mn to the base b. Meaning, if we are adding two logarithmic expressions, then we will be multiplying their respective powers. For the second property, it states that the logarithm of m to the base b minus the logarithm of n to the base b is equal to the logarithm of m over n to the base b. This implies that when we subtract two logarithmic expressions, then we divide their powers. For the third property, we have logarithm of m raised to n to the base b is equal to n logarithm of m to the base b. For this property, it implies that if the power has an exponent, then it becomes the multiplier of the respective logarithmic expression. The fourth property states that the logarithm of b to the base b is equal to 1. Here, we can see that the base and the power are equal. If this happens, then this logarithmic expression will be equal to 1. Number 5, the logarithm of 1 to the base b is equal to 0. Meaning, if the power is equal to 1, then the logarithmic expression will be equal to 0. This property came from the concept that for any base b, when we raise it by 0, then the value is always equal to 1. Finally, for the last property, we have the logarithm of b raised to x to the base b will be equal to x. Notice in here that the base and the base of the power is equal. If this is the case, then the entire logarithmic expression will be equal to this particular exponent. Let us use these properties in simplifying some logarithmic expressions. Simplify each logarithmic expression. For the first one, we have logarithm of x to the base 3 plus logarithm of 5 to the base 3. Number 2, we have 3 logarithm of x to the base 2 plus logarithm of 3 to the base 2. And for the third given, we have 2 logarithm of x to the base 2 minus logarithm of 3 to the base 2 plus 3 logarithm of x plus 1 to the base 2. Let us solve these examples one by one. For the first given, we have the logarithm of x to the base 3 plus the logarithm of 5 to the base 3 using the first property of logarithm, which states that the logarithm of m to the base b plus the logarithm of n to the base b is equal to the logarithm of mn to the base b. Then, this expression here, the logarithm of x to the base 3 plus the logarithm of 5 to the base 3 will be equal to the logarithm of 5x to the base 3. Recall that when we are adding two logarithmic expressions, then we are multiplying their respective powers. Then, multiplying x and 5, then we will be having 5x. Therefore, logarithm of 5x to the base 3 is the simplified form of the given. Moving on to the second one, we have 3 logarithm of x to the base 2 plus logarithm of 3 to the base 2. So again, we are given 3 logarithm of x to the base 2 plus logarithm of 3 to the base 2. Using property number 3, we can simplify the first logarithmic expression into logarithm of x cubed to the base 2, then copy the second term plus logarithm of 3 to the base 2. Next, since this is addition, so we need to multiply the two powers. Hence, we're gonna have logarithm of 3x cubed to the base 2. Therefore, this is the simplified form of our given. For our last example, we have 2 logarithm of x to the base 2 minus logarithm of 3 to the base 2 plus 3 logarithm of x plus 1 to the base 2. So, let us rewrite first our given here. So, we have 2 logarithm of x to the base 2 minus logarithm of 3 to the base 2 plus 3 logarithm of x plus 1
to the base 2. Using property number 3, notice that we have a number here and also here. So we will be using them as our exponents to the powers. So writing it, it will become logarithm of x squared to the base 2, then minus logarithm of 3 to the base 2 plus the logarithm of x plus 1 quantity cube to the base 2. Then, applying property number 1, since this is addition, then we simply need to multiply 3 and x plus 1 quantity cube. So, we will have logarithm of x squared to the base 2 minus the logarithm of 3 times x plus 1 quantity cube to the base 2. Next, since we have subtraction here, we need to apply property number 2, which states that we need to divide the two powers. So finally, we will have logarithm of x squared all over 3 times x plus 1 quantity cube to the base 2. Therefore, this is the simplified form of the given expression. Also, the properties of logarithm can be used to expand logarithmic expressions. Let us try to solve the following given. The first one, we have logarithm of 3x to the base 4. Number 2, we have the logarithm of 16 over x squared to the base 5. And number 3, we have logarithm of 10 over xy to the base 7. Solving them one by one. For the first one, we have the logarithm of 3x to the base 4. Since the operation between 3 and x is multiplication, using property number 1, when we expand this logarithmic expression, then it will become logarithm of 3 to the base 4 plus logarithm of x to the base 4. So this is the expanded form of the given logarithmic expression. For the second one, we have the logarithm of 16 over x squared to the base 5. Since this is division, by using property number 2, so we need to subtract the two logarithmic expressions with powers 16 and x squared. So it will become logarithm of 16 to the base 5 minus the logarithm of x squared to the base 5. Hence, this is the expanded form of the given logarithmic expression. And finally, for the last one, we have the logarithm of 10 over xy to the base 7. Since this is division, using property number 2, we will expand it by subtracting the two logarithmic expressions, logarithm of 10 to the base 7 minus the logarithm of xy to the base 7. Moreover, since this is multiplication, so we can still expand this logarithmic expression here, giving us with the logarithm of 10 to the base 7 minus the logarithm of x to the base 7 plus the logarithm of y to the base 7. Notice that I have enclosed them with open and closed parentheses because x and y are both on the denominator of the given expression. With that, simplifying them without the parentheses, we're gonna have the logarithm of 10 to the base 7 minus the logarithm of x to the base 7 minus the logarithm of y to the base 7. Therefore, this is the expanded form of the given logarithmic expression. I hope that you have understood the lesson. For the next video, we will discuss about logarithmic equations. Thank you so much for listening and see you on our next discussion. Good day everyone! In this video, we will discuss about solving logarithmic equations. These are the steps in solving logarithmic equations. For the first one, using the properties of logarithms, express the given in single logarithmic expression. Number 2, if needed, express the equation from step 1 into exponential form. Number 3, solve for the indicated variable. And number 4, check your answer. Let us try to solve some logarithmic equations using the provided steps earlier. For the first given, solve the logarithmic equation logarithm of x plus logarithm of 3 equals 2. As stated in step 1, let us express the given logarithmic equation logarithm of x plus logarithm of 3 equals 2 into a single logarithmic expression. Notice that we have addition here, so by using property number 1, we will be multiplying x and 3. So we will have logarithm of 3x equals 2. Next step, if needed, let us express this equation into exponential form. Notice that we do not have a base here, so therefore, it means that the base is automatically equal to 10 because this logarithmic expression is what we call common logarithm. Therefore, writing this logarithmic equation into exponential form, we will have 10 raised to 2 equals 3x. For step number 3, we need to solve for the indicated variable. Since we have 10 squared equals 3x, simplifying 10 squared, we will have 100 equals 3x. Since we are solving for x, we will be dividing both sides by 3. Therefore, the value of x is equal to 100 all over 3. Finally, for step 4, we will be checking if our answer is correct. To do that, we will be substituting x equals 100 over 3 to our given logarithmic equation, logarithm of x plus logarithm of 3 equals 2. So we will have logarithm of 100 over 3 plus logarithm of 3 equals 2. Combining these two logarithmic expressions, we will have logarithm of 100 over 3 times 3 equals 2. Next, simplifying 100 over 3 times 3, we will have logarithm of 100 equals 2. Next, looking at the expression, since we have a common logarithm here, automatically the base here is 10. Notice that for us to have 100 as our power, then 10 should be raised by 2. Hence, we have here 10 squared equals 100, therefore 100 equals 100, which means that the value x equals 100 over 3 satisfies the given logarithmic equation. For the second one, we have logarithm of x to the base 3 minus logarithm of 2 to the base 3 equals 2. Again, for step 1, we will be expressing the given logarithmic equation into single logarithm, and to do that, we will be applying property number 2 because we have a subtraction here. Since this is subtraction, it means that we need to divide x and 2. So we will have logarithm of x over 2 to the base 3 equals 2. Next, for step number 2, express the resulting equation in step 1 into exponential form. To do that, determine the base, the exponent, and the power from step 1. In here, we have the base equals to 3, the exponent equals to 2, and the power equals to x over 2. So writing it into exponential form, then we're gonna have 3 squared equals x over 2. Next, for step 3, we need to solve now for the indicated variable x. To do that, we need to simplify first 3 squared, which will give us 9 equals x over 2. To solve for x, we need to do cross multiplication. Since we have 9 here, so automatically the denominator is equal to 1. So when we do cross multiplication, we're gonna have 1 times x, which is x, equals 9 times 2, which is 18. Therefore, the value of x is 18. Finally, for step 4, we will be checking if our answer x equals 18 is correct. To do that, we will be substituting 18 to the variable x on our given. So we will have logarithm of 18 to the base 3 minus the logarithm of 2 to the base 3 equals 2. Since this is subtraction, so we will be dividing 18 and 2, giving us with logarithm of 9 to the base 3 equals 2. Writing this into exponential form, we gonna have 3 squared equals 9, and 3 squared is actually equal to 9. Notice that the left side is equal to the right side, which makes the statement or the given logarithmic equation satisfied. For our last example, we have the logarithm of x plus 3 to the base 5 plus the logarithm of x minus 2 to the base 5 equals logarithm of 2x to the base 5. Since we have an addition here, what we need to do is to multiply x plus 3 and x minus 2. So we will have the logarithm of x plus 3 times x minus 2 to the base 5 equals the logarithm of 2x to the base 5. Simplifying x plus 3 times x minus 2, we will have logarithm of x squared plus x minus 6 to the base 5 equals logarithm of 2x to the base 5. Notice in this equation that we have logarithm to the base 5 on both sides of the equation. If this is the case, then we can now simply cancel the logarithmic expression and equating the two powers x squared plus x minus 6 equals 2x. Remember that we only do this if we have logarithms to the same bases on both sides of the equation. If there is no logarithm on one side of the equation, then what we need to do is to write the equation into exponential form. Simplifying now this equation, we will have x squared plus x minus 6 minus 2x equals 0. X squared minus x minus 6 equals 0 will be our resulting quadratic equation. Since we have here a quadratic equation, therefore, we can solve the value of x by factoring. Factoring x squared minus x minus 6 equals 0, we're gonna have x minus 3 times x plus 2 equals 0. Equating both factors by 0, we're gonna have x minus 3 equals 0 and x plus 2 equals 0. Hence, x here is equal to 3 and x here is equal to negative 2. Since we have two values of x, we need to substitute these two values on our given equation here and determine which among them will satisfy the given equation. If x is equal to 3, then the equation will become logarithm of 3 plus 3 to the base 5 plus logarithm of 3 minus 2 to the base 5 is equal to logarithm of 2 times 3 to the base 5. Hence, we will have logarithm of 6 to the base 5 plus logarithm of 1 to the base 5 equals logarithm of 6 to the base 5. Remember that since this is addition, so we need to multiply 6 and 1. So we will have logarithm of 6 to the base 5 equals logarithm of 6 to the base 5. Therefore, x equals 3 satisfied our given equation. Checking for x equals negative 2, we will be doing the same thing. If x is equal to negative 2, then the equation will become logarithm of negative 2 plus 3 to the base 5 plus logarithm of negative 2 minus 2 to the base 5 equals logarithm of 2 times negative 2 to the base 5. Simplifying the powers, we will have logarithm of 1 to the base 5 plus logarithm of negative 4 to the base 5 equals logarithm of negative 4 to the base 5. Since this is addition, multiplying 1 and negative 4, we will have logarithm of negative 4 to the base 5 equals logarithm of negative 4 to the base 5. This equation seemingly satisfied our given equation. However, note that the powers should be greater than 0. Since we have here negative 4, therefore, we cannot consider the value since it is negative. Hence, the only value of x is 3. I hope that you have understood the lesson. For the next video, we will discuss about the first lesson for the quarter 2. Thank you so much for listening and see you on our next discussion.